Welcome back. So in this video, we'll be looking a bit further into what we can do with the Tracepoint eBPF application. This is the second part of my my eBPF with Rust and IIS series. If you want to watch the first part, I'll have it linked right here in the top right, and you can check that out if you want to learn about some of the history behind eBPF and how we got to the program that we're at right now. Anywho, so in the previous video, we had created an application where every time you run it, you would it would bind to the trace point that's called sys interconnect, and whenever we were to perform a curl, it would log it essentially. So if I was to curl google.com, it would add log lines to my terminal. Now let's look at some of the arguments that we have available at this particular point in the syscall. So just the way I had done it earlier as well, I'm going to go into sudo su, and once I've logged in, I can go into sys kernel debug, and I believe it's called events. It's called tracing events, and syscall sys interconnect. So this is a very hands-on sort of a code as you go kind of a video, but I'll have chapters linked down in the description below. So if you want to skip to some of the parts where it's sort of like checkpoints where we actually finish implementing a feature, then you can take a look at that as well if you want to skip through all of the iteration involved. Anywho, so now that we've reached here, I can do an ls, and there's a file called format here. I can take a look at that. So this essentially tells me the data that I'm receiving in the eBPF application. So I'm getting my, what's this called? I'm getting certain flags, common type, common flags, preempt count, common PID, getting the syscall number, file descriptor number, the address length, and the socket address. So now that I've got all of this, let's take a look at reading from all of these data pointers. We're going to start by logging the file descriptor number, because that's the easiest to log. So the way this happens is you've got a string of bytes that you've received, and it's your job as the programmer to let the eBPF application know which offset you want to read a particular data point from. So we've got that offset as well over here. So as you can see, since this is an unsigned short, that's of 2 bytes. So the offset is 2, and the next field right after that is another unsigned short, and the offset for that is going to be 2, since the size of the previous one was 0. Then moving forward, for the unsigned character, which is a common preempt count, the offset is 3 because the sum of all of the sizes of the fields that have come before it were 2 and 1 respectively. So building upon that line, we've come across to the point where the field that we're interested in, the FD, which is the file descriptor number, that is at offset 16 with a size of 8, and it's not a signed integer. So let's take a look at how we can parse that. From here, we can go into, we've got this, right? We can take a look at the trace point itself. If we take a look at the source code for the trace point, you can see it has a method called read at. So that essentially hints what we're trying to achieve in this application. Let's create a variable called let fd equals ctx dot read at. Looking back at the documentation, we can see that it is at position 16 with a size of 8. So we can read at 16. Now you probably noticed that it is throwing a lot of errors. So this is because it's an unsafe function. Since we're doing a raw memory access, Rust is not going to be happy with that. So we have to mark this as in an unsafe block, and we have to cascade the error upwards. So I'm going to convert this into i64, and make this return as u32. This is something I added later on, might not have been covered in the video, but you'll have to add as u32 here. Anywho, so now we've got our file descriptor number. Let's try printing it out. Let's take a look at what type has been assigned to it. The type is unknown, so we're going to have to assign a type to it. This is going to be a cint. And now that we've got the type assigned, let's print that out right here. fd Cool. So that's easy enough. Let's recompile our application and let's let it run. Cool. Now let's do a curl real quick. Curl google.com. And as you can see, we're getting the file descriptor number. So the first trigger over here was with file descriptor number 3. The reason behind that is every time you start an application, the first file descriptor gets assigned to std in, second one to std out. I believe it's the other way around. So you get the get file descriptor number 0 to std out, file descriptor number 1 to std in, and finally you get file descriptor number 2 to std err or standard error. I might have gotten those numbers mixed up, but the bottom line is that the first 3 are reserved. So every time you create a connection or you open a file, the first file descriptor that you'll get assigned will be file descriptor number 3. Anywho, so now we're getting data from the uh, application regarding the file descriptor number, right? So let's try something else. I'll go back into the definition of the trace point that we're looking into, and you can see that there's a field called the address length. So let's try taking this field out just because we're already here, so why not. Let's do a let, what's it called, it's called an addrlen. We're going to represent that as well as an integer, and that will be an unsafe operation, which is a ctx dot read at. The offset that it says here is 32, and let's print that in here in along with our logs. Cint, and I'm going to print this here as well. Oh, sorry, not cint, addrlen. Great. Okay, I can print this out, and if I go back and perform curls, you can see I'm getting the addrlen as well in the output. Along with that, if I perform a connection on IPv6, I will have a different output, different address length, because that is what, just a second, let me. So if I perform an IPv6 connection, I get a different address length because the addrlen essentially represents the size of the socket adder, the socket adder that's listed in the format. The sock adder right here. Now this is a sock adder. This is a pointer to a sock adder structure. Sock adder is an internal structure that the Linux kernel uses to signify the various kinds of sockets that you can have for performing network operations. And when you're performing a trace point, you can't really access the sock adder itself. You have an access to the pointer. You can just get the value of the pointer, but not the you cannot essentially dereference the pointer behind the sock adder. For doing all of those, we have U probes and K probes. We'll look into that in future videos. But for now, this is what we can do. Furthermore, we can check which application has performed this call, and that is a very simple operation. Let's write that in here. Let's say I want the PID and the thread group ID. All I have to do is take my context ctx and get the call the PID method on it and the TGID method on it, and it will get me the process ID and the thread group ID as well. So let's do the same thing once again. Cool. If I perform a curl, I get the output, and the same thing with a curl over IPv4. I'm getting the output with the process ID as well as the thread group ID for this application. Awesome. Now, what if I wanted to log all of this somewhere else? This is all well and good. You've got the user space application that is essentially printing out the logs for the kernel space application. However, there's another option where you can essentially log all of this into the kernel's log. We're going to take a look at how that can be done. So if you go into the documentation for IIA, let's go into IIA eBPF, and it's called a BPF underscore log macro. It's a macro, I believe. Let's see. Oh, sorry, it's BPF underscore print K. Right. So this is a macro that prints to a central location on your host machine. Let's take a look at that real quick. So we will print all of this. Let's do a BPF underscore print k, and we need to represent all of this as bytes. So the example over here is pretty good. I can just copy this as it is, and then I can substitute my values in here. Let's do this. Let's just copy all of this as a matter of fact. And all of these are digits, so these can be represented as %d. %d here, and we can add another %d here. Let's do fd addrlen ctx.pid and ctx.tgid. Now this is an unsafe function, so we have to wrap this in an unsafe block. Unsafe, and that looks good. Let's run this again. Awesome. So now we've got our application running. It's creating logs here, but it's creating logs in the central tracing directory as well. The tracing directory is also listed right here in the documentation. We can bring that into another terminal and paste this here. So as you can see, I'm getting those traces in this directory as well. So that's pretty cool. If you want to have some sort of a central logging for all of your trace points or all of your BPF applications, you can use the BPF print k method as well. So that pretty much wraps up everything related to Tracepoint that I wanted to cover. In the future videos, we'll be looking at k-probes and u-probes, along with how we can share data between the kernel space and user space. So it's all pretty exciting stuff. I hope you stick around for that, and thanks a lot for watching. I hope to see you soon. Bye-bye.